The last trick is to remember and know when you can use the number raised to log rule. It's quite useful, but sometimes we might forget about it because it might not be very obvious. So any positive number x can be written in this form, which is a to the power of log x base a. It's useful when both of the exponent and base have a variable. They don't have to be the same variable, but they just have to be both having a variable. So let's show how the left side becomes the right side. Just copy the left side, and then we can do this. So we can rewrite x as this, 10 to the power of log x base 10. That is equal to x. According to the formula above, we can do that. Then we can just, to make it cleaner, it will just be 10 to the power of log x. And that's log y on the outside. I will continue writing here. So we can flip where log x and log y are. So we can do this. 10 to the power of log y. And then log x goes on the outside. This doesn't change the equivalence. So now the inside becomes y. And it just looks like the formula we saw above here. And we can just ignore the base 10 right here because we don't have to write it. So that becomes y to the power of log x. And then we have showed how the left side becomes the right side. If you're curious about why x can be written in this form, I can quickly and informally show you how I understand it. So if you take log on x, you will just have log x. And if you take log for this exponent, you can simplify it and you'll get a result that will show that they're equivalent. So you can move this down, which means you will have log x base a times log a. So that means you have log x times log a over log a, which is equivalent to log x. So both will yield to log x if you take log on both of them, and then they must be equal. So that's how it works, according to my understanding. Now I want to talk about some harder examples and some extension problems that involve other tricks or just combines the tricks that I just mentioned. So the first example involves base unification and then double substitution to solve it. We can rewrite it in a way that will let us have the same base and then we can substitute stuff. This will be 4 times 3 to the power of 2x plus 3 times 2 to the power of 2x equaling 13 times 2 times 3 to the power of x. So what we can notice is that there's 3 to the power of 2x and 3 to the power of x, and then 2 to the power of 2x and 2 to the power of x. So we can have double substitution. Let a equal 3 to the power of x and b equaling 2 to the power of x. We can rewrite this as 4a to the power of 2 plus 3b to the power of 2 equaling 13, and then that is just ab. We can just move 13 to the other side, so that will be just 0 here. Then we just factor. So that will be leading to 2 cases. b minus 4a equals 0. That means 2 to the power x minus 4 times 3 to the power of x equals 0. So 2 to the power of x equals 4 times 3 to the power of x. So I'll just make it quicker, combining the rules we learned before, equaling, that's log 4 plus x log 3, because I just take log of this entire product, and then I just break them into the sum of two logs. Then x equals log 2 minus log 3, and that is log 4 on the right side. Then x1 is just log 4 over log 2 minus log 3, and that is just roughly negative 3.42. I will write it here and then erase it so we can write the other part, the other possible situation. The second situation, 3b minus a equals 0. That means 3 times 2 to the power of x minus 3 to the power of x equals 0. So 3 times 2 to the power of x equals 3 to the power of x. Then it's just log 3 plus x log 2 equals x log 3. And for the same reason I just explained for the previous occasion. Now we can just have x and multiply it by logs on one side and log 3 on the other side. That is log 3 minus log 2 equals independent log 3. And if you just divide log 3 by this difference, you'll get roughly 2.71 as the second x solution. This problem combines geometric series and logarithms, so if you don't know geometric series yet, you can skip it, or you can learn later and then look at this when you want. So I'll get into it right away. I assume you already know about geometric series. So we see that u1 equals 6, which is the first term, and r equals 2 over 3. So the sum to k terms equals to 6 times 1 minus 2 over 3 to the k's power, that entire thing over 1 minus 2 over 3, and that should be bigger than 17.8. Then we can just keep simplifying this. It will lead us to 18 minus 18 times 2 to the power of 2 over 3 to the power of k, and then that will be greater than 17.8, because 1 minus 2 over 3 is 1 over 3, and 6 divided by 1 over 3 is just 6 times 3, which is 18. And then this yields to 0.2 being greater than 18 times 2 over 3 to the power of k, because I just subtracted 17.8 from 18, and then I moved this term to the right side. Now we can rewrite this as 1 over 90 by moving 18 to the left side, which is greater than 2 over 3 to the power of k. So we can take a log on both sides and get k by moving it down, right? According to a trick we learned before. So that is just log 1 over 90 greater than k with times log 2 over 3 because we moved k down. And then now we have k alone on the right side, but we need to flip the sign here. Why? Because log 2 over 3 is negative, so we divide an inequality both sides by a negative value, the sign must be flipped. So that's why we have a minimum value for k, right? And then if we put it in the calculator, k minimum is roughly 12. This problem requires some algebraic skills and being familiar with the basic log rules, and also being able to recognize some quadratic features from what we will get later in this problem. So we can tackle this by writing it in a cleaner form without base 10 and without this fraction multiplying with an expression kind of form here. So we can definitely write it in an easier way to help us calculate. We just don't need to write base 10. And then we will move p plus 2q up, and then on the other side just 1 over 2 and then log p plus log q. So we can keep the left side as it is for now, but we want to do something on the right side to make it look less, well, lengthy. So this is the sum of two logs, and then we can write it as log p times q, then to the power of 1 over 2. And then you can recognize that this is equal to this. So we can just ignore log for now and then write their equivalence. You don't need to think about log for now, just solve them. So this square root is a bit annoying, so we can get rid of it by multiplying both sides to the power of 2. And that will give this. That will be 8 on the denominator. That is just PQ. So just copy the things in the numerator. And then that equals to 8 PQ if you multiply both sides by 8. And then you can simplify this by subtracting both sides by 8 PQ, and that is this, that equals 0. And this is a quadratic form, so we can definitely write it in a factored form, and it will yield to this. And it asks us to write p in terms of q, so p minus 2q equals 0. So p equals 2q, and that's it. And thanks for watching.